All right, welcome. Today we're going to talk about one of the most fundamental rules in the entire universe. It's the law that explains why time seems to only move forward and, maybe more importantly, why you absolutely cannot unscramble an egg. Let's get right into it.
So let's start with a really simple question, but one that has a super profound answer. Have you ever just stopped and noticed how some things in the world just happen? You put a drop of food coloring in water and it spreads out. A hot cup of coffee always cools down. But you never, ever see the reverse, right? You never see all that color suddenly gather itself back into one perfect little drop. So what is going on?
Okay, here's our first clue. Picture this. You've got a gas all packed neatly into one container. You open a little valve connecting it to an empty container and whoosh! Of course, the gas instantly expands to fill both. It happens on its own every single time. But think about it. Have you ever just watched a gas-filled room and seen all the molecules decide, hey, let's all go hang out in that one corner? No way. It's a one-way street.
And here's a clue we've all experienced probably while making breakfast. An egg falls. It breaks. It's a classic, irreversible process. But the reverse, a splattered yolk and shattered shell magically reassembling into a perfect egg and hopping back in your hand? I mean, it's not just unlikely, it feels fundamentally impossible. We know in our bones that's not how the world works. There is a definite direction to how things change.
So, this universal one-wayness, what do scientists actually call it? Well, they've got a specific term for it, and that term is a spontaneous process.
Now, in science, spontaneous doesn't mean it just happens out of the blue for no reason. It just means that once the conditions are right, a process will go in one particular direction all by itself without you having to constantly push it along. And the most important part? It's irreversible. You can't just rewind the tape.
And okay, this is a huge misconception we need to clear up right now. Spontaneous does not mean fast. An explosion? Yeah, that's spontaneous, and it's pretty much instantaneous. But you know what else is a spontaneous process? Rusting, and that can take years. The timing doesn't matter, it's all about the direction. But here's where it gets really interesting. That one-way street I mentioned, turns out the direction isn't always set in stone. It can actually flip depending on the environment. Just think about ice. Above 0 degrees Celsius, ice spontaneously melts into water, no question. But if you drop the temperature below 0, the spontaneous direction completely reverses. Now water will spontaneously freeze into ice. This tells us that conditions like temperature are absolutely crucial.
So this brings us to the real heart of the mystery. If things like temperature can flip the direction, what's the deep underlying force that's actually calling the shots? What is driving all of these one-way processes?
So what is it? Why does nature seem to prefer the gas spreading out? Why does it prefer the broken egg? The answer is a concept that's, well, it's beautiful, that's incredibly powerful, and it can be a little confusing.
The answer is entropy. Simply put, we often call entropy a measure of disorder or randomness, but a much better way to think about it is as a measure of possibilities. The more ways there are to arrange the parts of a system, the higher its entropy. It's all about options. Let's jump back to our gas in the containers. When all those molecules are jammed into just one flask, there's a pretty limited number of places they can be. But the second you let them into both flasks, the number of possible spots, the number of possible arrangements just skyrockets. The system naturally moves toward the state with the most possibilities, the most randomness, the highest entropy.
And this isn't just a casual tendency, like, oh, things kinda like to be messy. No, this is a fundamental law of physics. The second law of thermodynamics states that for any spontaneous process, the total entropy of the universe always goes up. Every single time an egg breaks or a gas expands, the entire universe gets just a tiny, tiny bit more disordered. This, right here, is the arrow of time.
Okay, so that's the big cosmic rule. The universe loves disorder. But how can a chemist in a lab use that? How can we predict if a reaction is actually going to happen or not? Well, for that, we need a more down-to-earth practical tool.
So it turns out nature is basically in a constant tug of war. There are two major tendencies that are always battling it out. On one side, you have that drive towards more disorder that we just talked about. But there's another really powerful force pulling in the other direction. And that second force is enthalpy. That's just the drive for things to get to a lower, more stable energy state. You can think of it like a ball that always wants to roll to the bottom of a hill. It's seeking stability. So you've got this cosmic showdown, the push to release energy and get stable versus the pull to spread out and get disordered. And this beautiful little equation is what settles the fight.
It's called Gibbs free energy, or delta G. It masterfully combines the change in energy, delta H, with the change in disorder, delta S, and it even factors in the temperature, T. And here's the bottom line. If the final number for delta G is negative, it's a green light. The process is spontaneous. It's going to happen. If it's positive, red light. No go. It's as simple as that.
And we have this man to thank for it, J. Willard Gibbs. He was an American scientist back in the 1870s who figured out how to put energy and entropy into one single, all-powerful equation that can predict the direction of change. Just incredible.
So what's the big payoff for understanding all this? Well, once you get a handle on these forces, you can actually create a complete map for any substance, showing you exactly how it's going to behave under pretty much any condition you can think of.
And this is what it looks like. It's called a phase diagram. Think of it as a cheat sheet for matter. All you have to do is pick a temperature along the bottom, pick a pressure along the side, and this map tells you exactly what you'll have: a solid, a liquid, or a gas.
And here is where it all connects so beautifully. You see those lines that separate the different states? On those exact lines, our Gibbs free energy, that delta G value, is exactly 0. It's the tipping point. It's a perfect equilibrium, where the drive for low energy and the drive for high disorder are in a perfect stalemate. So on this line right here, melting and freezing are happening at the exact same rate.
And that brings us to something that is truly weird and wonderful, the triple point. It's this one single, unique combination of temperature and pressure where all three phases, solid, liquid, and gas, can all exist together at the same time in perfect harmony. It is a point of perfect three-way balance.
And look, this isn't just some abstract theory for exotic chemicals in a lab. Here's the phase diagram for plain old water. Everything we know and rely on about water, its freezing point, its boiling point, the fact that you can boil it faster on a mountain, it's all right here on this map, all governed by that delicate dance between energy and entropy.
Which really just leaves us with one final, fascinating, and kind of mind-bending question. If the entire universe is on this unstoppable one-way street heading towards maximum disorder, maximum entropy, then how is it even possible that something as incredibly complex, structured, and ordered as a living thing, as you, could ever exist in the first place? Something to think about. Thanks for joining me.